Welcome back. In this video, I'm going to prove the theorem of the parallel gradient. So here, assume that f has local extreme value on the constraint level curve C at a point P. Okay, so which means that f is the surface multivariable function whose graph is a surface. Okay, we assume that the x comma y must be must lie on the curve C. Okay, so and then we assume that f has local extrema, a local extreme value at points P. The P is on C. Then the first statement, gradient f is orthogonal to the line tangent to C at P. The second statement, gradient f is parallel to gradient g, which means that gradient f can be expressed as the scalar multiplication of gradient g. And then that scalar, lambda, is called the Lagrange multiplier. Okay, so that theorem is called the parallel gradient. So the simple case for the function f and the constraint curve C. So here you see the circle. These are the level curves of f, and then increasing z values and moving away from the origin. Okay, and that the red curve, that's the constraint level curve C. And then the equation C, and the function is denoted by g of x comma y equals 0. Okay, so from there we observe that two things. F has a local extrema at point P on the constraint curve. The second one, gradient f is parallel to gradient g at point P. Okay, so why? Because let's see. The first one. So we're gonna prove the first assertion. So now we first we parameterize the constraint curve C. Okay, so g of x C because here we assume that actually g is smooth. The curve is constraint curve is smooth. So which means that that the g of x comma y can be expressed as parameterization. Okay, so r of t is equal to x of t comma y of t, and then x and y must be differentiable. Otherwise, the constraint curve, level curve, will not be smooth. Okay, so p of a comma b is x of t naught and y of t naught, so which means that when the parameter t is t naught, then the x and y equal a and b respectively. Okay, and then we take the second step. See, we're gonna take a derivative f with respect to t. Okay, you see that here now x and y are function of t. Okay, so now I told you what the function f is the what x comma the x and y function f will be chosen from the x comma y on the curve. Okay, right? So now the x and y are the function of t. So we can say function f is a kind of function of t, right? So we take a derivative f with respect to t. Then we have to apply chain rule because the f is kind of the most outer function, x is kind of middle function, inner function, right? So we take a derivative f with respect to x times partial x partial t. Okay. Similarly, we do this for y. Then this one can be expressed as gradient f, dot product of gradient f and r prime. Right. Now, then since f has a local extreme value at p, right, which means that df dt derivative of f must be 0, right? Okay. So at t equal t naught, the df dt must be 0. Okay, which means that what? But df dt is this, right? So which means that this is 0 at t equals t naught, which means that these two guys are orthogonal, right? So, and then r prime is a tangent vector on C, right? Because r prime is a tangent vector. The gradient f is orthogonal to the line tangent to C at point P, yes. Okay, so these two guys are orthogonal, but since this is the tangent vector on C, that means gradient f is orthogonal to the line tangent to C at point P. Okay, let's see the proof of secondary assertion. So because the constraint curve C is also a level curve of the surface Z equals g of x comma y. Yes. So I don't know what that is, g of x comma y, but definitely there exists the surface, a function of surface g of z equals g of x comma y, and that's the one of the curve of that surface, right? So then gradient g at a comma b at p is orthogonal to C, right? All right. So now then the second one, by the first assertion, gradient f is orthogonal to C at P. You see that these two guys are orthogonal to the same curve C at P, which means that what? Those two guys must be parallel. That's why there exists a real number such that gradient f is equal to lambda times gradient g. Right? Okay. So that lambda, that real number, is called the Lagrange multiplier. Okay. So that's it.